Now we want to focus on some useful properties of K-connected graph. So for general K-connected graph, finding some simple and easy to understand characterization of them do not exist. The ones like year decomposition or the vortex split for three connected graphs. I mean, those are the easy to understand operation which characterize all two connected graph and all three connected graph. Of course, the higher four connected graph or five connected graph, they are all two connected and three connected. So they also admit the same, same way to generate. They can be generated by the same way. They can be generated by the year decomposition, or they can be generated by vortex split. But those operations only captures their three connectedness or two connectedness, not the K connectivity. So, in order to properly understand the difference between this four connected graph and three connected graph, say, then we don't have such a simple way to characterize four connected graph, which separates them, which distinguishes them from just three connected or just two connected graph. So instead of that, we want to rather obtain some useful property of this K-connected graph. Especially we want to consider about connection property. As seen before, finding paths between two vertices are a very natural problem, which requires the usage of the graph. In many situations, we can model the problem using graph so that our final goal is to find certain paths between two specified points. And those graphs which can be done was defined to be the connected graph. And then now we have a K-connected graph, which essentially says that such a connection is possible after deleting K-1 vertices. And instead of consider this as finding paths after deletion of K-1 vertices, another natural way to quantify them was finding many paths between them. Possibly, the natural way is to find the paths that does not use the same vertex or maybe same edges. Okay. Give me a moment, let me apply phone before the lecture that I should have been. Anyway, so we want to also consider this natural property. So here, finding a path after deleting vertices. Here, finding paths, many paths between them. And we say those paths in a way that disjoint except the end vertices. If you think about it a bit, and this one is actually stronger property. If you have this disjoint path, say 4 disjoint paths, and no matter how you choose 3 vertices, you can only destroy 3 of them. The one remains. So this property implies the other. This bottom one is stronger property. And this already shows that if we can ensure such paths, such collapsible paths, it will be useful. just having one path actually deleting certain number of vertices. And then here many paths which are disjoint except the end. We can already see, or we can already feel that this might be more useful in many scenarios. So our goal is to find, so as I mentioned, this implication is easy, and we want to also show that the other implication. This was the definition of K-connectedness, but we can actually use in this form, in this more useful, possibly more useful, upgraded form. So that's what we want to prove. And we want to prove strongest form that we can use, meaning that we want to prove all possible variations that we could obtain. One of them is for, say, digraph. For digraph, we can also consider the same way when all the paths are directed paths. So we want to also consider this directed graph and undirected graph together. Let's use the definition. Let's introduce the definition. For digraph, we didn't define what K-connected means. We only define it to be, the concept of the strongly connected. So we defined that a digraph is strongly connected if it contains a path from each vertex to every other vertex. And we define it to be K-connected if it has more than K vertices, so which is, again, same technical condition. And we say that the emitting fewer than K vertices always is a strongly connected diagram. And we define the connectivity kappa of this diagram D is the maximum K such that E is K-connected. And also let's define that for non-empty proper subset S of the vertex set of this diagram, we define the edge code. And we write as S bracket with the S and S complement. This is again the set of edges from S to S complement. For example, if you have a S and the S complement, then we have, say, this. Then the edge cut from S to S complement only contains the red edges. Blue edges are not there. And we say that a digraph is KH connected if every edge cut has size at least T. Again, what this means is that if you delete less than K edges, it is still strongly connected. So now what we do, we want to define some parameters and concepts related to these two different kinds of connectivity. Here, what was the main goal? Here, the main concept is separation. We want to delete vertices to separate these two. How many vertices do we need? Here was the robustness of the connection. Here, we want to find many disjoint paths so that we can ensure many ways to connect them. So let's define. So for two vertices, which are non-adjacent in G, okay, so maybe now we defined for the connectivity for graph or digraph. And now, in the rest of this, section, while we are dealing with this K-connected graph, and what we are gonna do is, in this video and next video, is something called the Mangel theorem. While we are dealing with this Mangel theorem, we let G be either multi-graph or simple graph or multi-digraph or single digraph. So G could be any one of them. And if this digraph and xy here means that the edge from x to y. If it is not the digraph, it is just the graph, then it's an edge between them. And for any of them, the following definition and statement later will make sense. And what we define on x, y separating set is a set F which does not contain x or y, such that once we delete it, there are no paths between x and y. And we define the parameter measuring this separation, how difficult it is to separate them. We use kappa xy to be for the minimum size of the such and set, the xy separating set. And we say the paths from x to y are independent. If they share no internal vertex. Sometimes we call it the internally disjoint. But let's use the words independent, meaning that you take the first path from x to y, then except x to y, the rest of them are internal vertices, and you take the other path and other path, and so these vertices, they are all distinct. Then we say that this is independent. And we write lambda xy to denote the for the maximum number of independent xy paths. Okay, now we have defined it. And now we can write down an inequality which implies this. And that can be written as kappa of xy is as big as or bigger than equal to lambda xy. Because if there are 3 independent paths here, so no matter how you delete 2 vertices, one remains intact. So in order to separate x and y, you need to delete at least 3 vertices. So this inequality holds. And also, this has close relationship with connectivity. What's the connectivity? When you connectivity, you need to measure the size of set, the minimum size of set, which separate the graph into, making the graph into disconnected graph. Then what happens? You have this separating set, and then delete it, and then you have 2 components, and there must be some vertex here and here which are separate. That means, because if connectivity is a minimum parameter, it's a minimum out of all possible x and y, such that x, wait, y, it's, give me a moment, suddenly my pencil doesn't work. Let me try again. So xy is not a match. For any pair of non-adjacent one, you consider this kappa of x and y, and then take the minimum. And that's the same as the connectivity. And then what's our goal? Our goal of achieving this equivalence, we want to prove equality here. We want to show this equality. That's our goal. So in order for that, we need to first prove a theorem. And then later we want to prove this inequality for graphs and diagram. And we will define H version of this parameter. And then we will prove the equality for H version. That's our goal. That will give us the ability to switch between these two freely. So when we deal with the K-connected graph, we have an additional tool. Whenever it's convenient for us, we switch from the separation point of view to finding this independent path point of view. So which will be very convenient for us. In order to prove it, now we define some concept. So this separating set is very natural, but it's slightly, inconvenient point of this is that this is not an arbitrary set. This is a set avoiding x and y. So we want it to be more, relaxed, so that we can use it more freely. So we define the following concept. And also, one more point is that here we only care about the separation between x and y. And then this xy has to be non-adjacent. And those are a bit technical condition, which doesn't feel too intuitive at the first sight, and then it's not really convenient for us. So we want to generalize this concept so that it's more useful, and then we can freely use it. So instead of finding connection between 2 vertices, we want to consider more general thing. So between 2 sets, we want to find the paths. And while doing that, we want to consider the separating set, which may use some starting point or ending points that we wanted to connect. So that's 2 different things. instead of connecting two vertex, we want to connect set to set. We want to find the many passes connecting one vertex from here to here, another vertex from here to here, which are all disjoint, not just internally disjoint, not just independent, which are just collection of disjoint passes. And this separating set we also upgraded so that it could be any set, even containing these vertices that we wanted to connect is allowed. By considering this concept, it will be, more convenient to prove what we want. Then it will be more general. So for any two sets, we say that on X, Y path is a path from X to Y. So starting from one vertex of X to one vertex of Y, it is a strict XY path if it visits X and Y only at the end. So this is a efficient connection. For example, this is an XY path, which starts at the vertex in X and which ends at vertex in Y. But this is actually not efficient. We could take this shorter path. This is more efficient way. This other part was not really necessary there. So JXY path is a more efficient path. And we define on XY barrier is a vertex set C such that this G minus C has no XY path. So here we didn't say this is disjoint from X or Y. So X itself is a XY barrier. Because if you delete every vertex in X, then now there are no paths from X to Y. And we say that on XY link is a set of pairwise disjoint strict XY path. So now we have defined the concept. Then what we can prove is following theorem by Kim. In either graph or diagram C. So before I mentioned that it's either multi-graph or multi-digraph. So here, we don't have to actually consider multi-graph in this theorem, because again, in here, we are only considering about vertex connectivity. So having multiple edges doesn't make any difference. So what happens? The minimum size of an XY barrier is same as the maximum size of an XY link. So this is similar to what we want to prove, but has a slightly different form, as instead of considering the independent paths and the separating set, we are considering barrier and link. So in this variation, we have the equality. That's what this. Then after proving this, we will use this to prove what we want. So let's prove this. What we will do, we use induction on the following parameter. The number of vertices in G plus number of edges in G, we use induction on this. If this parameter is, what's the base case? If this parameter is 1, that means G has at most one vertex. Then the statement becomes trivial because the maximum size, minimum size are both just 0. Or depending on x and y. So if there is one vertex and then x and y are same, then okay, the minimum size of xy barrier is 1, maximum size of xy link is 1. The empty path, the one vertex path is what we wanted to find. So we let, so assume we had more than one vertex, and this parameter is bigger than 1, and we let k be the minimum size of an xy barrier in G, and assume k is at least 1. If k is 0, then there is nothing to prove. So we consider two cases. Case 1. G has an xy barrier C of size k other than x or y. You have x and y. Okay, this picture might be misleading. Due to our definition, there is no reason that x and y have to be disjoint. There could be x and y same. But in that case, it's one vertex alone forms a path from y x to y. It's a path of rank 0. So it's actually helping us. So what's our basic strategy? Our basic strategy is that find G, which separates from x and y. This is xy barrier. In such a case, what we want to do is we want to show that this G actually partition the graph into two, G1 and G2. Edges in here, edges in here. Then each of the graph is smaller than G, so we use induction to find the xg link and then gy link, and then together they form xy link. That's our basic direction. And how do we prove it? Just this G blocks y from x. So so this is xy barrier, means every path from x, y pass through G. Every xy path intersect G. So what happened? No xg, no strict xg path. So as I mentioned, we want to partition these two into two graphs. And we have to actually prove that we can actually take these two graphs which only intersect at G. For that, what we have to do is we consider that if you have a strict xg path that doesn't intersect strict gy path outside G. So if you take xg path and then strict yg path, If they intersect in here, that what happens? Then you could go here and then you take this path and you find the path from X and Y which does not meet any G, which is contradiction. So this doesn't hold. So it's either this way they are disjoint, or they share the endpoints in G only. So that G1 and G2 be the subgraphs of G which are induced by the vertices on any strict XG passes and on strict CY passes respectively. So that defines this G1 and then G2 as we wanted. Then we have that the vertexes of G1 and vertex of G2 intersect at only G. Then what happens? Since this G is not X or Y, and K is at least 1, both G1 and G2 has fewer vertices than G. So the vertices in Y does not belong to G1. The vertices in X does not belong to G2. Unless, they are, some vertices belong to the G, then it's okay. But okay, let me rephrase it. The vertices in G minus G, X minus G does not belong to G2. And then vertices in here does not belong to G1. Yes, G is not X or Y, so both graph lists at least one vertex, so they are smaller than G. So what we know, since this every XY path hits G, what do we know? Every XG barrier in G1 is an XY barrier in G. So you have X, G, Y. If you have a XG barrier in G1, so by deleting this, X can never reach G. Then if in the entire graph, if X have a path from X to Y, avoiding this red part, then it cannot meet G because this one is XG barrier, but somehow if you miss it, then it's a contradiction that G is an XY barrier. So every XG barrier is also XY barrier in G. But what do we know? We assume that the G had no XY barrier of size at least K. So size at less than K, so as G1 has no XG barrier of size K minus 1. Then by the induction hypothesis, what? G1 has no XG barrier of size K minus 1, and then that means it's, if you use this induction, that means the minimum size of XY barrier is at least K. That means there are XY link of size K. G1 has an XG link of size K. Similarly, G2 has an GY link of size K. And then G itself has size K. So they meet at C to form a XY link of size K. So case 1 is done. What's case 2? It has no XY barrier of size K other than X or Y. So the only XY barrier of size K in G is X itself or Y itself. Then, using the symmetry, assume that the X has size K. Y could be bigger or, but bigger or same. If X is a subset of Y, then what? The desired link, we can find the desired link consists of passes of length 0. We can just take the one vertex path for each vertex in X, then that's already done. Otherwise, what? We have X, and then some of them are Y. There must be some vertex here, which is the lowercase x. We select X in this set. Then what we know is that S minus X does not block Y from X because it has size K minus 1, so it's not XY barrier. There is a path from, so let me write it that once we delete everything in X except this X, it has strict X Y path. So let's take such a path, and then let's say the first edge is between X and W. It begins alone on edge XW with this W is not in X. And now what we consider? We consider G prime, which is what we get after deleting the XW from G. And consider the G prime is the smallest XY barrier in this G prime. Okay. Now what we want to show is that in this graph, we delete one edge, right? We consider some cases whether it has in here the G prime has a size at most K minus 1 or K. If this has size at most K minus 1, we can add W to get a barrier of size K in original graph G. Because deleting this edge or deleting this vertex have the same effect. Only the deleting vertex has a stronger effect. And so if G prime is smaller, then we will do that. If G prime has the same size K, then what? We can use the induction hypothesis. If G prime has a smaller number of edges, then our induction was on the number of vertices plus number of edges. It has same number of vertex as G and smaller number of edges. And the induction hypothesis, IH induction hypothesis, it provides an XY link of size K in G prime and also in G. So we are happy. If G prime is smaller than K, then what? And G prime itself is not XY barrier in the original graph G. So there is some XY path in G avoids this G prime. And such a path does not exist in G prime. That means every such path uses the HXW. Hence, what? G prime union with X and G prime union with W are both XY barrier in G. But what do you know? Both of them are having size K. They have size and most K. Then what do we know? We are in the second case. Such a barrier has to be X or Y. The hypothesis for case 2 is that G prime intersection, union with X is X, and G prime union with W is Y. That's the only possibility. So how does it look like? X and Y, X, W, H it, and then this. But what? In this case, the problem is easy. We take the one vertex passes in G prime. We take these one vertex passes and we take the one path, XY path of length 1 that forms the desired XY link as we wanted. So this proves this Pim's theorem, showing that the minimum size of an XY barrier for any X set X and any Y, any set Y, the minimum size of XY barrier has the same size as the maximum size of an XY. And then what's our goal? We will use this to prove what we wanted, the separation set, the smallest size of separation set, and then largest size of the event passes between two vertices are same. We will prove that in the next video. But the basic idea is that if you have X and Y, you consider all its neighbor, and then you delete it vertex. Because now you identify all its neighbor. There is no way to reach this vertex avoiding this. And then what you do, you consider the remaining graph, and then you consider this set as X, this set as Y. Then size of XY barrier is same as the XY separating set. And then the independent passes between X and Y become same as XY link. So using that, we will prove what we want in the next video. And also we want to define the H version of this, and then we will prove all the things together. That's what we will do in the next video.